Firstly, thank you very much for the invitation to come and speak to you today. It's a real pleasure to give one of the keynote presentations for the conference, and I hope you've found the conference really informative and enjoyable. In this presentation, I'm going to go over some of the technologies that we're developing in my lab at the University of Manchester, focusing on wearable devices. Wearable devices, of course, have many applications in sports and sports technology, and I'll take a look from a technical point of view on where we're looking to go next with some of those. So what I wanted to do was start off by giving just a little bit of background, setting the scene for where I'm coming from, where I'm sitting from in my lab. And then I've picked out 3 or 4 different areas to probe into a little more depth, but also kind of quite high level, just to try and connect some of the different dots together. Before doing that, I would like to give the acknowledgement at the start of a talk, because of course there are many people, many different collaborators, many different funding bodies who have all supported this work. You can easily get to more than 100 people probably who have contributed to different parts of this. As I said, I'd like to just start off by giving a little bit of info about background on myself and the motivation that I'm looking for in my lab, where we're looking to go. So firstly, just for those of you who don't know Manchester, we're based in the UK and we're one of the UK's largest universities. Internationally, I would always tend to assume everyone's heard of Manchester because people are either into the football, and of course we've got two very well-known teams there, or they're into the cricket. But those things do, in terms of sports, really do put us onto the map as an important international place for innovation and sports technology. And then to introduce myself, I'm an electronic engineer by background, so looking at kind of microelectronic circuit design. And I spend kind of most of my time in the University of Manchester in our School of Engineering. But actually I've got quite a few different positions. So a lot of our work is focused on more medical applications of wearable devices. And so I've got an appointment in a medical school. I also have an honorary appointment in our National Health Service. And then in the UK, we have what are known as national institutes focusing on different technical areas. And so actually my office these days isn't in the university, it's in what's called the Henry Royce Institute. And that's our national institute for material science. So how do we make kind of materials that are flexible, stretchable for electronics, and we'll see some of those later in this presentation. And I also have a position in what's called our Alan Turing Institute. So that is the National Institute for Data Science and Artificial Intelligence. So really kind of applying machine learning techniques to some of the wearables, some of the sensor data that we're collecting. And my lab is really looking to be kind of cross-sector, cross-disciplinary, having multiple kind of positions in order to not be siloed into a Department of Engineering, but working across lots of different areas, which is what we really need for success in this space. Now, focusing in on my kind of technical background, what we've got on the screen here is my cross-section of a wearable device. And really it's about kind of getting data from you, that's about your heart, your activity levels, whatever, up to the cloud through some electronics, and then potentially back again. This might be through behavioural change, motivating people to be more active, that sort of thing. And when I started working in this area, more than 15 years or so ago now, it was very much in the hardcore microelectronics, making low power circuits to enable the sort of wearables that we now have. Back then, the power consumption was too high to have very portable wearable devices. If we fast forward to now, my lab's got activity across that complete spectrum. doing work on all of the different parts of the system that we need in order to make a step change in our wearable technologies. Some of these are kind of more clinically, medically focused. Some of these are very relevant for kind of sports applications. And I'm aiming for kind of half an hour, 40 minutes or so here. I can't go into depth in all of these topics, so I've selected out a few of them in order to speak about. And within that, my lab today would work on general wearable devices. We've got a lot of work on wrist-worn wearables, on foot-worn wearables. Actually, we've also done a lot of work, and we're probably best known for our work on brain sensing wearables, so letting us get information about your brain kind of out of a lab in the real world. And that might not sound super relevant to some of the kind of sports applications that we're thinking about in this conference, but I'm going to come back to that at the end of this presentation, because I think there is a lot of overlap in terms of brain interfacing and sports related wearables. But first, let me have a look at the kind of wearable element itself, the electronics fundamentally that goes into a kind of a wearable device, and talk about the work we're doing there. So this is a selection of wearable devices that you could buy off the shelf today. One of these is actually my personal wearable device. I'm a relatively keen runner and would use one routinely for tracking kind of pace and heart rate and whatnot. And I'm sure that many sports people would be using a wearable device in order to do quantified self, to record some of their biometrics, to do pace-based training, to do heart rate zone-based training. And wearables have meant that it's never been easier to do that sort of thing. And of course, in some ways, wearable devices like that are a mature, commercially available technology. You could go out and buy one of these relatively easily off the shelf. In other ways, there are lots of open opportunities for making them even better. So, for example, in improving the battery life, there's very common feedback that users have. It's a pain essentially to have to charge devices every day or every week or however often it is. There's lots of ongoing work about enabling more sensing modalities. And that's often when a lot of people come to me when they want to measure parameter X, and it's not possible for whatever reason in a current device. And of course, closely linked to that is the accuracy of many current devices. And of course, this varies across the board, but the general advice is often it's about the trends in the data. Are you doing more steps today than you were yesterday, sort of thing, rather than necessarily the absolute number, where there can be kind of relatively big error bars on that. A particular interest of mine is about trying to get more individualization, more personalization, because we've got a selection of wearables on the screen there, but in many ways they're very, very similar. They all look extremely similar. They're all measuring more or less the same things, and there's opportunities there for saying actually, but the users aren't all the same. They have different preferences, they have different user experiences, they have different goals. And how do we get some of that personalisation in terms of the physical unit, in terms of the sensing that's done, in terms of the feedback that's given, and so on. So lots and lots of opportunities for making next generation wearables. Just showing some examples of kind of custom electronic devices that have been made in my lab, and we can see straight away how these are for all different parts of the body. So we've got a standard kind of watch worn factor. There's kind of electronics for the electroencephalography, which is when we measure signals from the head coming from your brain, and then also kind of smart insoles, so foot-based sensors. And we are seeing more of those emerge commercially, but when we started in that sort of space, it just wasn't possible to buy the sort of sensing that we wanted to do at the feet. And again, I'll speak about some of that foot-based sensing later on in this presentation. If I zoom in on one of those, we've been doing a lot of work recently about wearable light sensing. Now, because this, of course, is really important for all manner of different applications, because your light exposure really sets your body clock, your circadian rhythm. And there are international standards for how to measure the sort of light exposure that your eye receives. So not light in general, but particularly how your body is responding to the light. And that sort of sensing wasn't available in kind of off-the-shelf devices. And so we've had a project running in kind of designing custom wearables for measuring that sort of parameter. And you can easily see how this relates to kind of sports and technology applications, partly for training, but not least for doing international competitions, for kind of getting your body clock into the right place when you just kind of jetted halfway around the world, as it were, for doing your international competition. And so kind of making that sort of customized electronics for what people need to measure for their particular application, that'll be relatively kind of bread and butter activities for my lab. Going beyond that, what we've been doing for a long time now is looking at kind of how do we go beyond kind of current wearables. So what we've got on the screen at the moment is kind of my timeline of kind of all technology development. And it starts before this. We could have a box on here from the 1970s, and we'd have a mainframe, the size of this room, kind of thing. And it's only approximate, but roughly every decade we've had a step change in the miniaturization of our electronic devices. And so current wearables, those devices we're using to inform our training at the moment, really emerged with Fitbit, with the Apple Watch that came out in 2014. The next step beyond that is kind of envisioned as what I've called kind of conformal electronic devices here. Sometimes they're called epidermal devices, but devices which attach directly to the skin, and so they get a really good contact. They're very lightweight, they're very socially discreet, and lots of really advantageous factors. That one on the right hand side there isn't kind of one from my lab, but it represents the general sort of space that we're looking at. So if we take a look at an example on some of the boards that we've been doing in my lab, we've got those on the screen here. So in this panel, for example, we've got an electrode which is for electrical sensing from the body. So something like electrocardiography for heart rate. And what we know there is that the surface area of the contact determines the quality, the signal quality that we can collect. And so this sort of very conformal epidermal contact following the contours of the skin can give us a really high signal quality compared to something that's sitting on top of the skin, like a conventional rigid bit of electronics would be. We've got some other examples on the board here, so illustrating the sort of flexibility that we're getting in some of our devices. And important for our designs here is that these are all designed to be scaled up. So a real focus in my lab is not making one device at a time, but making sure these things are designed, tested and similar to be compatible with roll-to-roll, in this case manufacturing, something where you can make hundreds, thousands of them at a time. And that sets some of the design decisions, some of the spacing considerations that we have to put in. And so if I zoom in onto one of our boards here, it's actually transparent, so it's on a kind of yellow background to help show it up. We can see some of the detailed design that's gone in, and really, of course, there's a lot of know-how behind the scenes here to know how to do kind of two-layer boards where we can have tracks crossing over one another, how to do the component mounting, how to do that in a way that is compatible with scale up. What this sort of board will do is things like activity sensing, so kind of there's an accelerometer on there, and then also kind of heart rate, so kind of electrocardiography, as we mentioned a minute ago. And so nothing necessarily too exciting from the sensing point of view. You can buy devices off the shelf that will do that right now. But the idea is that then forms our base platform for adding in more and more sensing technologies. So we've published just recently about adding in sweat-based sensing, looking at things like lactate, potassium, that sort of thing, onto the same underlying platform. And of course, where we want to go in the future is trying to look at more sustainable electronics, looking at the removing some of the metals, some of the plastics that are going into our current devices. But as I say, this acts as a line in the sand. We can do kind of sports relevant sensing. We can start to do that at scale with flexible devices where we can make many of them at the same time. And then we can use that as our base to add in further sensing, which you can't do at the moment. In our manufacturing, all of that is based upon printed electronics. So we're doing screen printing mainly in those slides you just saw, because that's very compatible with routes to scale up. But also we have a particular interest in printing because it gives avenues for personalisation. You see this a lot with kind of 3D printing of bespoke devices, and I don't have time to go into a lot of detail in this particular presentation, but looking at how can we make devices go beyond one size fits all, making sure that they get the best kind of connection, size, shape for everybody is a really important direction in this area. So let me jump from that, which is our kind of general directions in terms of the hardcore engineering for where our next generation wearables going. Let's take a look more at kind of using some of our wearables and what our thinking is there. So here in my lab we've done a lot of work about foot-based sensing. So not placing devices on the wrist like we would normally, but trying to put them embedded into smart shoes, I guess would be the fundamental term. And there's a few reasons why we might be interested in doing that. One is about social discreteness, right? So almost always while doing kind of sports applications, people will be wearing shoes, right? It's not another thing to put on. It's not another thing to accidentally get knocked or accidentally hit somebody else. It's something which is already there as a part of the person. You put your shoes on and it's ready to go. Actually, a big driver for me was about power autonomy. So there's long been an interest in self-powered wearables, right? So that's the idea that we can do energy harvesting. So kinetic watches have been, self-winding watches have been available for a very long time. So typically they have a moving mass, and the motion of your wrist means that it generates enough energy to power the mechanism. And that sort of thing ought to be really ideal for wearable sensors in sports applications. People are running about, say, they're generating lots of heat, they're generating lots of motion. And the fact that that's why they want a wearable, to monitor their status, gives this kind of positive feedback loop where we ought to be able to use that energy. Now, in practice, that's easier said than done. Powering just an analog watch mechanism like a self-powered watch needs very, very little power. That can be done robustly and has been possible for 20 or more years. Even the lowest power wearable needs quite a lot more power than that, and there really is a big gap to overcome. And so what we wanted to try and say is, okay, well, where can we generate the most power? And of course, it turns out it's not the wrist, it's at the feet. because your feet have, they have the complete body weight compressing them down. They have the kind of the maximum amount of movement as you're walking, running, whatever. And so, ought to be a really good place for doing self-powered wearables. Now, of course, within that, there's two challenges. So one is, well, how much power do we actually get? Is saying that we get the most from the feet. How much more do we get? Is it like 1%? It's probably not worth it. Or is it like 10 times, 100 times? And then also, we don't often do a lot of wearable sensing at the feet. So what do the biosignals look like? What can we get out? If we tackle the first of those questions firstly, so just looking at, well, how much energy can we collect at the foot compared to, say, the wrist? Well, we did a dedicated experiment for that. So we 3D printed some custom insoles. So this is placing an accelerometer device kind of under the arch of the foot, and asked 12 people to kind of walk on a treadmill at different speeds, so we can estimate the amount of energy that we can collect. For doing that, this is a model that has been published previously by others, and it's based upon what's called a kinetic energy harvester. So this is when you've got a moving mass, and when it moves between two plates, you can generate some power from that, and there's a well-established model for, given how much movement there is, how much power do you get out the other end. And so what do we find? Well, firstly, of course, at the foot, we get twice the amount of acceleration compared to other parts of the body. So in terms of, if we got our moving mass, a kinetic-based energy harvester, we've just got kind of twice the amount of acceleration present to drive that movement. So that's a good start, right? That our input is twice as big. But what we also find is that the frequency spectrum of the movement that's present is different. So if we look at the wrist, what we find is that the movement is concentrated very much at one frequency, at that fundamental frequency. And so when you're designing an energy harvester, you've got to make sure that it collects very well at that frequency. And what that means is that you've got to have a very untuned harvester, because we don't know the exact frequency that someone's going to be moving at. It's got to be able to respond to quite a few different ones. In contrast, at the foot, there's a lot of energy in several of the harmonics. And so even if we're a little bit mistuned, say our optimal harvester was here, we're still going to pick up quite a bit. And so not only can the input be kind of twice as big, for the same harvester, which has a certain bandwidth at its input, we're going to pick up energy from more harmonics, giving us more energy to collect. And so putting those together, what we find is that yes, the foot gives us factors of 10 or more energy to collect. It really empowers us in terms of doing self-powered energy harvester based wearable devices. So here we're collecting up to kind of 15-20 milliwatts of power, which is definitely enough for running a wearable device in a self-powered way. And here we're not accounting for some of the optimizations we can do at the foot, because if you're using the whole of the insole of a shoe, say, you potentially got a much bigger space that you can use compared to a wrist-worn device. But we don't take that into account here. So that's good. That's really positive news in terms of kind of enabling next generation self-powered, no battery wearables. Of course, what we need to do next is that second question of looking at, well, what do the biosignals look like? What can we measure at the foot? And of course, there's things like gait and whatnot. But in terms of the other modalities, the ones we might not think of naturally as being done at the foot. So here we're looking at heart monitoring and doing that using photoplethysmography, PPG. So this is exactly the same as your smartwatch would do. So it's shining a light into the body, measuring the amount of reflection, and that goes up and down with the heartbeat as blood flows through your body. And I think it's very well known that the PPG is extremely sensitive to motion artifacts. And this is why it took quite a long time to get it into wearable devices. It's why green LEDs are often used, because it gives the most motion robust signal. You need lots of signal processing, even at the wrist, in order to differentiate the kind of heart component from the motion component. And that only gets worse at the foot. So the further motion that we highlighted earlier, well, that's now a bad thing in terms of doing the sensing. Right. So the picture that we've got on the screen here, those big peaks, they're not the heart rate. That's someone walking, that's someone taking steps. A clean PPG, which has the heart rate, if you were to zoom in, you'd be able to see it very clearly in that blue line. But it's really tiny compared to the amount of interference that's present from motion. And we're dealing with a signal processing case where the signal to noise ratio is minus 50, minus 60 dB. Very, very little signal there compared to the noise. But here's a zoom in of that, just showing that you can see the heartbeats very nice and clearly if there's no motion present. And then showing the signal that we collect while people are walking. So this is a PPG signal, so it's an optical measurement. What I think is very interesting about this is that it is very repeatable. So often we do kind of gait measurements with an accelerometer, gyroscope, that sort of thing. Actually, there's probably some interesting things to look at in terms of the optical measurement that we get and how we use that to get additional information on gait. But that's not the primary aim here. The primary aim is to, under all of this interference that we're getting, can we extract the actual heart rate that's present. I won't go into too much details on the signal processing, but we put together a adaptive filter based algorithm for doing that, so measuring the motion and using that as a reference signal to subtract off from the PPT signal. And this is fundamentally what's done in many kind of wrist-based implementations. And what we get is a little bit of a mixed bag. The error is fairly high, but not necessarily a lot higher than doing the same thing at the wrist. We spoke earlier about the accuracy of some of our wearable devices, and there are error bounds on those. We find that the ankle and the foot don't make a lot of difference. There are just cases where it really just kind of doesn't work at all. But I thought a really interesting case to draw out in terms of this conference, just for looking at some of our thinking for how do we do things differently. Where can we put our sensors that will give us novel information? How do we overcome some of those challenges, particularly around powering in this device? And I think we've made some good progress there, if there's still work to do. As a last topic, and I won't spend too long on this, but I wanted just to go back to some of our brain interfacing work. Because I think at first glance, this might not kind of sound like it's in scope, but actually I think there's lots of interesting things there. So firstly, I would describe this as neuromodulation. And that's when you kind of stimulate the body, typically using some form of electrical based stimulation. It might be magnetic, it might be sound, but it's driven by electronics fundamentally, in order to modulate the nervous system. I'm particularly interested in non-invasive options, so we've done a lot of work about electrical stimulation of the brain, but also just sound stimulation, visual stimulation, those sort of things that can be done very easily, very portably, possibly on a smartphone, based platform. And a lot of my interest in this space comes for applications in chronic pain. And of course, it's not ideal, it's not what we'd want, but there's lots of overlaps and uses of pain-related technologies in sports people. I mentioned earlier I'm a keen runner, but I'm not doing any of that at the moment because I've injured my foot. And some of those rehabilitation technologies I think are really important, and neuromodulation plays a potential role there. So over the years we've made a number of different platforms for doing brain stimulation, electrical stimulation. Today we focus a lot on the more kind of right hand side here, so looking at what can we do on smartphone based platforms, things that we could give to people in the wild. So for example, that might be doing neurofeedback. I believe this is very popular in some kind of golf applications and just kind of more meditation type, getting into the right state sort of applications. But this is when we kind of monitor your brain activity. We kind of pass the data to a mobile phone in real time. So there's a wireless link from an electrode here to a mobile phone. And then we measure typically what's called the alpha power. And that's just a particular rhythm that you get in your brain. I wouldn't worry too much about it in detail. But we then present a visual dial to somebody. So if they've got more alpha, the dial goes in one direction, and if they've got less, it goes in the other direction. And of course, one of the things about neurofeedback is that it's then up to the person to decide what to do. So it's not kind of driving the person, it's just giving feedback, and it's up to that individual to come up with strategies for how do they get the dial to go where they want to go. This is an in-lab study, but looking at the regulation that we ask people to do, of course we see changes in self-reported pain state. Now this is quite early stage work, there's a lot more to do here, but very important as part of the spectrum of sports technology for helping, I say, with that rehabilitation, that recovery from injury type space. And we have that going now on a mobile phone based platform, so we can do this kind of not in the clinic bringing people into a hospital, but out in someone's home, in a hotel room if they're at a competition or whatever. And I think we're going to see lots and lots of stuff in this neuromodulation space in forthcoming years. So I've got work around what's called sleep engineering, and we're looking at kind of memory performance in that project. But there are people looking at aspects of, say, wake-up freshness. Again, really important for sports people kind of travelling across the world for competitions. And that's what I wanted to go over in this presentation. I've deliberately touched on a few areas, not necessarily gone into depth in some of them or kind of covered all of the different areas, but what I really wanted to convey is how we're trying to work across a number of different areas. And I think by connecting some of these different areas together, between having next generation flexible wearable devices, having potentially closed loop stimulation of the person, so it's not just about getting data, it's really about using it. How we can have next generation wearables which are really very different from the devices that we have available now. Cool. Thank you very much for listening, and I hope you enjoy the rest of the conference.